And I've been asked to kind of continue this introductory kind of vein, in this introductory vein, and talking about this title is Doing Science with Multimodel Ensembles, but I'm going to start out by just reviewing some best practices, the kinds of things that people do or are encouraged to do with multimodel ensembles. And I'm going to show some examples from the IPCC era 5 of the kinds of plots that you can make and the types of ways that people just kind of depict results from multimodel ensembles. And then because I'm giving the talk, I'm going to give some examples from our group of some science that you can do with these multimodel ensembles. So one of the interesting things about a multimodel ensemble average is that a multimodel ensemble average generally outperforms any individual model. And this seems kind of mysterious, but it's been seen in numerical weather prediction, it's been seen in ENSO prediction, it's been seen in simulations of 20th century climate, it's been seen in detection attribution, some variability statistics, systematic biases, and this is kind of a figure that you've seen, or I've seen a lot. This is from this Reichler and Kim paper, and they were comparing various phases of CMIP, just going up to CMIP 3, and the idea is that the further you are to the left on this plot, the better the simulation is. And this is a multivariate metrics they put together, combining, I think, 10 or 11 different things like temperature, precipitation, wind, sea level pressure, things like that. And the black dots are the multimodel ensemble average. You can see that the black dots tend to be the farthest to the left, which means that's producing the best simulation. And the individual circles here are the individual models. So this is kind of an interesting feature of multimodel ensemble averaging that you can use to your advantage in a number of different ways. I think it's not really well understood why this happens, but one idea is that the models do more good things in common than they have errors. So the errors tend to cancel out when you average them together. The good parts of them tend to come out, and that's why you get these better simulations. There was a workshop held here in 2010 organized by Reto Canuti, who's going to give a talk later this week. He's from ETH in Zurich. And he organized this workshop in this room and invited a lot of people. And the idea was that there was kind of a lot of confusion about what the best practice, there's Reto right there actually, what the best practices were for actually using these multimodel ensembles. Because people were faced with, after CMIP 3, this large number of models. Each model had different numbers of ensemble members. How do you cope with all this? And so, kind of the first question that people ask is, how do you produce a multi-model average when there are multiple ensemble members of different sizes for each model? So model A may have 10 members, model B may have 5 members, model C has like 3 members. How do you deal with this? Well, the default that came out of this workshop is you include all the models. So you take all the models and you average them in 2 different ways generally. Either you take one realization from each model, so one ensemble member from each model, average those together, or you average the ensemble members from each model together. So if model A has 10 members, you average all those together. If model B has 5, you average all those together. And so you come out with kind of one ensemble average for each model, and then you average those together. And so those are the kind of the 2 ways that people generally deal with these multimodel ensembles. There are other ways, and other people have tried different things, but that's kind of the best practice, is kind of default. Another question people have is, well, there's all these models. In CMIP 5, there's over 40 models. I just want to look at the best models. So show me what the best 5 models are, and I'll use those. And the answer is there is no best model generally, because depending on the metric you use to evaluate a model, you'll get a different ranking based on different metrics. So some models do better with precip, some models do better with sea level pressure, some models do better in certain geographical areas. And there really is no way to say, okay, what the best model is. Or there was always ideas about, well, in CMIP, maybe we should have some kind of a threshold bar of simulation quality where we reject models that don't meet that threshold of simulation quality, and then you come back to this thing, well, how do you do that? Because depending on the metrics you use, you get a different set of models. So you're back to the default of using all models. So that's usually the default. But There's also a way you can subset models. So say you're looking at a certain specific feature or geographical area. Say you're looking at, say, the Indian monsoon. If you can make a physically justifiable reason for subsetting or taking a subset of models, for example, if you're looking at the Indian monsoon and you say, well, these 5 models do better at simulating Indian monsoon precipitation than all the rest, and therefore I'm interested in looking at Indian monsoon precipitation, so I'm going to take this subset of 5 models. That is also kind of a justifiable best practice if you can come up with a physical justification. But having said that, there are some new efforts being made by a couple of the people that are going to be speaking at this workshop to weight models in various ways. So instead of tossing models out that are bad, you basically come up with a ranking and you weight those models when you're doing the multi-model ensemble average. And Ben Sanderson and Reto Knuti have been working on doing that, and I think they're going to be talking about that in some combination in their talks later in this workshop. There's something called emergent constraints, which is an interesting twist to how you can look at model fidelity, and I'll say a little bit about that in a minute. And the other thing is when you're comparing a multi-model ensemble average with some kind of spread to some observations, the best practice now is to try to include more than one observational data set because there's uncertainty in the observations. So you don't have just one absolute final thing you're trying to compare to. There's uncertainty, different observational data sets usually have somewhat different values. And so now you see people are usually trying to quantify the uncertainty in the observations compared to the uncertainty in the model simulations. And Ben Santer, I think, is going to talk about that on Thursday. Here's a plot from one of Reto's papers. This is just showing that models are getting better. This is an evaluation just based on 2 features of the simulation, temperature and precipitation, going from the CMIP 2 models at the top there, the CMIP 3 models in the middle, and the CMIP 5 models at the bottom. You can see there's more models now that are appearing in CMIP 5 than were appearing before. The multi-model mean is this red line. The multi-model median is the dashed line. You can see that the better the simulation, the shorter the bars are. So the closer you are to the left the y-axis, the better the simulation. And you can see that these bars are getting shorter, meaning the simulation quality is getting better. But in this paper, this is a really great quote that Reto came up with in this paper, and the quote is, most models are strongly tied to their predecessors, and some also exchange ideas and code with other models, thus supporting an earlier hypothesis that the models in the new ensemble, meaning CMIP 5, are neither independent of each other nor independent of the earlier generation. So this is kind of this model independence idea that's going to be discussed at this meeting, and it kind of comes to bear in things like this, where, and this is from a couple of papers, this has been Sanderson and Mike Weiner, who's back there, and also Ben Sanderson and Reto and Peter Caldwell. This is going to be input into the U.S. National Assessment that's just starting up, and they've come up with a way to weight models. And the weighting is a function of model independence, which is the x-axis at the bottom there, and the fidelity of simulating a kind of a multivariate set of criteria or metrics over North America, because this is the U.S. National Assessment, so they're interested in trying to weight models that have the simulations of various things over North America. And I think either Mike or Ben or Reto is going to talk about this more in their talks. There's another interesting feature that's kind of come around in the last few years called emergent constraints. And this is another way to kind of evaluate a multi-model ensemble. And the interesting thing about this is you're trying to look for something in the observations can give you some clues as to how well the models are simulating something. And usually you try to find a metric in the climate system that incorporates a feedback and some kind of temperature response. But you can use this in a number of different kind of applications. But the one that's usually cited is, I think, the first time that this was done. This is by Alex Hall and Chu that was in this paper in GRL in 2006. Where they noticed that if you look at the springtime snowmelt, in other words, you look at the temperature difference in spring, and you look at the change in surface albedo in the spring from observations, you can relate that to similar calculations from the models. So you've got something in the observations you can tie to the models, and this temperature albedo change response is something that gives you an idea about snow albedo feedback. And then you can actually calculate in the models from a future climate change simulation a temperature change and a future climate change from increasing CO2 and the corresponding change in surface albedo. And that's plotted on the y-axis there. And the x-axis is this so-called seasonal cycle, which is the temperature change in spring divided by the change in the albedo change divided per unit per degree K. And you get this kind of interesting relationship between the models that is kind of almost linear. And the good thing about this is that you actually know what this value is for the observations for this seasonal cycle, and that's this value right here. And you can come up here in this line, and you can say, okay, these models that are somewhere near this intersection of this regression line with this observational line are probably the models that are giving about the right value for this climate change feedback parameter. And these three models here seem to be the best at, from this metric, at getting this kind of relationship. And this idea of emergent constraints is something that's being used more and more in a lot of different, using a lot of different quantities. And so this is kind of a new way of looking at multi-models. So Jean-Francois mentioned this is kind of what's become a traditional depiction of a multi-model result. Plots like this have appeared, I think, in every IPCC assessment, at least the three most recent. This is just a time series of globally average surface air temperature change from a number of different models. This is from CMIP 5, this is in the IPCC Air 5. In this depiction, this starts in 1950, and you have all these models. The multi-model average is the black line, and this uncertainty range is the 5 to 95% range, which is plus or minus 1.64 standard deviations to give you an idea of the spread. The number here is the number of models, so 42 models contributed to this time series, and then you go into the future. This is RCP 8.5, the high scenario, and RCP 2.6, the low scenario. 28 models here, 32 here. And again, the same kind of uncertainty ranges are plotted here. And so this is kind of something that everybody's used to looking at. The unfortunate thing about a multi-model ensemble average is when non-specialists look at this, they think this is actually what's going to happen. The temperature change is going to be nice and smooth, ascending very uniformly into the future to some really nice, smooth state. But of course, that's not true because that's just the multi-model ensemble average. The thing about a multi-model ensemble average is you're averaging out the internal variability by definition. The internal variability is randomly occurring in each model ensemble member. So when you average that out, all these randomly occurring instances of natural variability get averaged out, and you're left with the externally forced response. And so you end up getting this really nice, smooth depiction of basically the increasing CO2 going into the future, but the shading indicates that there's a lot of variability in these individual model simulations. And here's an example of subsetting, again from the IPCC Air 5. The question was asked, roughly when would we expect to see a nearly ice-free Arctic in September? And if you looked at all of the simulations of Arctic sea ice, that's the shading is the same kind of thing. You see a huge range. You see a lot of models that are doing various different things. But when you look at the individual model simulations, they all had a lot of them had pretty sketchy simulations of Arctic sea ice. Some had too much Arctic sea ice, some had too thick Arctic sea ice, some had too thin Arctic sea ice, some had really bad trends from the observed record. And so this was an example of making a physical case for subsetting. So the question was asked, okay, which models gave the best simulation of something we've observed? So, okay, let's pick the models that have close to what the average sea ice thickness is, and which models had roughly the trend of the shrinking sea ice during the observed record. And there were 5 models that met that criteria, and those 5 models then get plotted in this kind of red shading. The red shading is actually the full range from these 5 model simulations, ensemble members. The ensemble average of these 5 models comes down here, and you can see it crosses this dashed line here. The dashed line is what sea ice experts define as a nearly ice-free Arctic in September. There are nooks and crannies where various sea ice bits stay in and really never melt, but basically the bulk of the Arctic is ice-free. And this conclusion, or the conclusion that came from this, is in this bullet here on the bottom that was in the summary for policymakers, based on an assessment of the subset of models that most closely reproduce the climatological mean state. In 1979 to 2012 trend of the Arctic sea ice extent, a nearly ice-free Arctic Ocean in September before mid-century is likely. Yeah, medium confidence. So there's an example of subsetting based on a physical reason for subsetting and selecting a subset of those models. But when you actually plot out all the individual model ensemble members, you get these kind of spaghetti plots. And this is an example from chapter 9, where we were addressing, and you notice there's multiple observational data sets, these heavy dark colored lines, the observational data sets, several observational data sets. You can see that there's some spread in the observations. The question was this so-called early 2000s slowdown. And you can see that the observations kind of are on the lower end of this spread of the ensemble members. And so this was sometimes been called the early 2000s hiatus. And there was a lot of debate over the wording for this in the summary for policymakers. And it came up with this is due roughly equal measure to reduced trend and radiative forcing, cooling contribution from natural internal variability, mainly the negative phase of the interdecadal Pacific Oscillation in the Pacific, and includes a possible redistribution of heat within the ocean. So there was an example of trying to use model simulations compared to observations to understand something that was happening in the real system, and I'll say more about that in a bit. Another way you can use these multi-model ensembles is they're not just run with all forcings for 20th century, they're run for either single forcings by themselves, in other words, just sulfate aerosols and everything else held constant at pre-industrial values, or just solar variability, or just greenhouse gases. And in this case, there was sets of experiments made with just natural forcings, in other words, just solar variability and volcanic eruptions. That's the blue shading in this kind of a plot. And then you add in the anthropogenic influences, the increasing greenhouse gases and changes in sulfate aerosols and ozone and things like that. And this is a relatively familiar picture that shows the multi-model ensembles with the ranges, the spread defined as we did before. The blue or purple shading is the range from the basically the no humans planet, in other words, just natural forcings. And when you add in the anthropogenic forcings, you get the pink shading. The black lines are the observations, and you can see that there was 3 different observational data sets used there, and some of them, they're almost indistinguishable depending on the region. Some of them do have some spread. But nearly every region, the only way you can get the observed warming that we've seen is to add in the anthropogenic influences. In other words, the pink shading generally encompasses the observations, the black line, while as the purple shading with just natural forcings doesn't. This is a long-standing result, and again, using various configurations of multi-model ensembles from the CMIP 5 data set. Now, these single forcings can be interesting in a number of different applications, both in detection attribution and trying to understand, in this case, an example from our group, trying to understand the interaction between the externally forced responses and the internally generated variability. So in this case, we used a 5-model ensemble, 5 models that had single forcings of just sulfate aerosols only, greenhouse gases only, and then long pre-industrial control runs to see what the internally generated variability was. So basically, this is the first EOF of sulfate aerosols only. It's got this pattern. The PC time series is going down. So basically, all these areas here are going to get cooler as the aerosols increase over the 20th century. Greenhouse gases are kind of warming everywhere. And the internal variability here, this is the first EOF of low-pass filtered sea surface temperatures from these 5 models. And it has this kind of interesting El Nino-like pattern that resembles this pattern, which is the low-pass filtered EOF2, actually, from the observations. EOF1 is the trend. This is kind of taken to be the pattern of the interdecadal Pacific Oscillation. And you can see that there's a high degree of correspondence between these 2 patterns, suggesting that what we see in the observations is probably mostly internally generated, because the only way you get this pattern out of a long pre-industrial control run where the forcings aren't changing is by internal variability. And so this is kind of leading the way to how do these externally forced parts interact and are manifested in the climate system with this internally generated variability. And this kind of question becomes relevant when you look at this kind of a plot. This is a plot of observed annual mean global surface temperature, annual surface temperatures. This is from kind of a version of the Tom Carl et al. Paper from last summer. And if you draw a trend line, in this case, if you draw this trend line here from 1950 up to present, but 2015, I think, you see this nice, smoothly ascending trend. This long-term trend looks like that's pretty much all that's going on. But if you draw trend lines based on the phase of the interdecadal Pacific Oscillation, or IPO, in the Pacific, the red trend lines are when the IPO is positive, meaning sea surface temperatures in the tropical Pacific are a little bit warmer than normal. The blue trend lines are when the IPO is negative, when the tropical Pacific sea surface temperature is a little bit cooler than normal on decadal timescales. You get a different kind of perspective on what's going on. So you can see that the actual evolution of what's happening, the time evolution of what's happening, is some combination of this internally generated decadal variability superimposed on this long-term warming trend from increasing greenhouse gases. And so that concept, this interplay between the internal variability and the external forcing, is something that you can use this multi-model ensemble to look at. And again, this is an example from our group. This is just a plot of one ensemble member from each of the 40-some models. I think 42 models are the gray lines here. Here's 3 observed data sets to kind of give you an idea of what the uncertainty is in this time series going from the late 1800s up till 2015. And if you draw these lines on the phase of the IPO, the positive IPO was basically from early 1900s to the early 40s. Negative IPOs from the 40s to the 70s, positive IPO from the 70s to the late 90s, negative IPO from roughly 2000 up until probably 2 years ago. You can actually then ask the question, how much of these epic trends are due to just the external forcing? How much is due to something that we can identify in the system that we think is producing this variability, which not too long ago we just called noise. We would not even want to think about internal variability because it was just, we didn't even want to go there because it was just too hard to try to figure out what was going on. We were interested mainly in the externally forced response and the human influence on climate, but when you're doing things like decadal climate prediction, where you're trying to actually predict the time evolution of climate over the next decade, you're actually trying to predict the noise and you're trying to predict the externally forced response. It's that combination that gets really interesting. And so what we tried to do in this paper, which is about to come out in 2 weeks or so, is we tried to say, okay, let's take the CMIP-5 multi-model ensemble, average it all, do a multi-model ensemble average, and get the trend for this time period here from, in this case, for each phase of the IPO. Let's just look at this as an example. This is the positive phase of the IPO from in the early 1900s. And this is the multi-model ensemble median, actually. The black line is the median, and we got this box and whisker depiction here to give some idea of the spread. And we're defining that as what the external forcing is giving us. But the observations are these dots here. There's 3 dots. You can barely see them there. And you can see that there's a disagreement. The observations, the trends in the observations is greater than the externally forced response. So the question is, how much does the IPO contribute to this difference between the externally forced response defined by the multi-model ensemble average and the observations? And so we take a long control run from one model, because we want to just pick out trend lengths from a single model simulation. In this case, we used CCSM4 1100-year control run. Made distributions of when you had global surface temperature trends based on phase of the IPO, got a distribution for negative IPO phase, distribution of trends for positive IPO phase, and actually did a correction to these trends using the IPO phase, and we get to this distribution. So now the median of this distribution is a lot closer to the observations than the multi-model ensemble average, which is the externally forced response, and we can say that we get closer to the observations to the tune of about 71% of this difference can be accounted for by this internally generated decadal climate variability, the noise, right? So this is what we want to look at, and then you can do this for each of the IPO phases. It's 25% in the initial phase, and this big height is from 41 to 71, 75% from 71 to 95. 2 different time ranges for the most recent period. Surprisingly, only about a quarter of this difference between the externally forced response and the actual observed trends are accounted for by this pattern of the IPO as defined by the model. And again, the caveat is this is a model defining this pattern from a control run. But this actually points to the fact that there's probably been contributions from things like a series of moderate-sized volcanoes, changes in stratospheric water vapor, and some other factors. So that's just an example of using a multi-model ensemble average to define the externally forced response. You use a long model control run to give you an idea of what the internal generated variability is, and then you can figure out how much of the difference between the actual observed trends and the externally forced response is being accounted for by this one particular decadal internally generated process. Here's one of my favorite quotes from a politician recently. This is a quote from the senator from Oklahoma. He made this quote he stated this in a U.S. Senate hearing in January of 2014. And he said, temperatures have flatlined over the past 15 years, and to my knowledge, not a single climate model ever predicted the pause in global warming would ever occur. Now, to give him the benefit of the doubt, I think he was probably thinking of the multi-model ensemble average. And that is correct, because the multi-model ensemble average, as we've seen in previous depictions, actually shows a warming when the observations are kind of in that lower end of the range of the model simulations. But let's just check to see if he was actually right. So what we did is we actually looked at the CMIP 5 set of ensemble member simulations from 40 plus models. There were 262 possible realizations of 20th and 21st century climate when we were just using RCP 8.5 to go into the future. And we looked for simulations that had exactly the observed temperature trend from 2000 to 2013 at exactly that same time. And it turns out 10 out of 262 realizations got the observed temperature trend, in other words, hardly any warming over this time period, versus the others. And the multi-model ensemble average obviously would keep on going and have disagreement with the observation. So you get 10 out of 262. The reason it's only 10 is it's only by chance that the internal variability in an individual ensemble member happens to match up at exactly the right time, at exactly the right magnitude with what actually happened in the observations. So the observations are going along, generating this internal decadal variability. The model is going along and simulating its own internal variability. And if you happen to get them synced up, 10 of these happen to sync up at exactly the right time. And it turns out that if you look at the surface temperature trends from these simulations, this bottom panel here, you see these blue colors. It's the negative phase of the IPO. And it's pretty significant, showing this kind of cooler conditions on these over this time period over the tropical Pacific. So that kind of is consistent with what we know, what we think we know about how the tropical Pacific on decadal timescales affects global surface temperature trends. And it shows that the models do have the right processes in them to simulate these kinds of things. Models can get this, but in these long uninitialized simulations that start in 1850 and run all the way through to 2100, it's really only by chance that you happen to sync up the internal variability at the right time. This is kind of a complicated figure, but I just wanted to illustrate this. This is another paper we've done, just appeared last month, where we were trying to address this conundrum of the Antarctic sea ice. So as we all know, the Arctic sea ice has been decreasing at a rapid rate, as expected. Climate's warming up, ice is melting, it all seems to make sense. Models seem to show that. So that all seems to be pretty consistent with our physical understanding. But the Antarctic was going the other direction. Antarctic sea ice was expanding. This was widely cited, has been widely cited by the denier community as something seriously wrong with the models, because all the models show that Antarctic sea ice should be decreasing. And indeed, the multi-model ensemble average does show Antarctic sea ice should be decreasing. But let's just look at this box here that I've highlighted. This is from some observations. And so this is plotting trends in Antarctic sea ice by season. And this is now for this period 1979 to 99. And we can see that there's been some slight increases. The red bars here are increases. March, April, May is really the only season that gets a significant increase. These error bars here are the 5 to 95% limits. There's actually been some decreases in December, January, February. Not much, but really not a whole lot going on in this period. But when you go after 2000, these are the trends from 2000 to 2014. Now you get these really large increases in all seasons. They're statistically significant in 3 out of 4 seasons. And so there seemed to be something that changed between this period up to 1999 and this period after 2000. What changed at that time? The IPO transition from positive to negative. And we saw that that has effects on global surface temperature trends. It apparently had some kind of effect on Antarctic sea ice. So this suggests that perhaps this expansion of Antarctic sea ice is internally generated decadal climate variability. It's not externally forced response. So when you look at the model simulations, these are the model simulations, the multi-model CMIP 5 model simulations of Antarctic sea ice. This is from this earlier period, 79 and 99. The blue bars, all seasons show a decrease of Antarctic sea ice. If you looked at the same plot from 2000 to 2014, it'd be the same. All models and the average would show a decrease. But if you look at these models here, and again, these are these 10 realizations that had the slowdown at about the right time and had this negative phase of the IPO. If you look at those 10 models, you get big increases of Antarctic sea ice. In other words, this appears to be in the models. The models are capturing this internally generated variability and the effects of Antarctic sea ice in the same way that seems to be happening in the observations. You just have to look at it in the right way. And this, again, is kind of the dangers of just looking at a multi-model ensemble average versus trying to understand what some individual ensemble members are doing when you're looking at this connection between internal variability and externally forced response. Just a couple other interesting little plots here. This one up here is the trends and this is a polar projection, so Antarctica is in the middle here. South America is kind of sticking in here from the left-hand side. The blue colors are where there's been trends in, positive trends in sea ice extent from this period 2000 to 2014. This is for June, July, August. You see similar pictures for the other months. You see a little bit of decreases of Antarctic sea ice over here, but when you look at the sea level pressure anomalies, again, these are observations, the contours of sea level pressure anomalies, and if your eyesight is really good, you can see little arrows. That's the surface wind. But of course, what's happening is this feature here, the Amundsen Sea low, which is kind of the analog in the southern hemisphere to the Aleutian low in the North Pacific. The Amundsen Sea low has been getting more intense over this time period. And that means, because the circulation is going around the low in a clockwise fashion, you're getting surface winds over here in this area that are blowing away from Antarctica. So these surface winds are pushing the sea ice out away from Antarctica. As it's pushing the sea ice out, more sea ice fills in behind because it's still really cold, and you're expanding the edge of the sea ice. And you can see over here on this side, here's an anomalous high, and you're seeing the same kind of thing. You're seeing this, the winds are pushing the sea ice away from Antarctica, and that's where you're forming increases in sea ice extent. Same thing over here. So this doesn't seem to be a thermodynamic thing. It's a dynamic kind of response. And it even kind of has a bit of a wave train kind of character to it with this Amundsen Sea low there where the L is, the high up there in the Weddell Sea area, and kind of a series of highs and lows going around Antarctica. So this seems like there's a dynamical forcing to these changes in sea ice, which is pretty interesting. Well, where's it coming from? Well, our hypothesis was that the IPO changed to negative during this time period. That means you have below normal sea surface temperatures in the tropical Pacific. That means you have negative precipitation anomalies. That means you have negative convective heating anomalies. We know that convective heating anomalies in the tropics drive anomalous Rossby wave responses into the mid-latitudes. This has been known for quite some time. So we were able to trace this back to the tropical Pacific in this plot here in the lower right. We used just an atmosphere-only model and just put in a specified convective heating anomaly over the tropical Pacific, that it was in the same sense as what we observed during the negative phase of the IPO. And this is the pattern we get. So we get this big deepening of the Amundsen Sea low, anomalously low pressure over here. Surface winds are all blowing out away from Antarctica. You get a little bit of a high over here, meaning you're getting winds blowing toward Antarctica here, warm air advection, which would contribute to those decreases in Antarctic sea ice. Another bit of a low over here, which would again contribute to some of this surface winds blowing away from Antarctica. And so this kind of teleconnection pattern we can trace back to the tropical Pacific and the phase of the IPO. So our story is that this was internally generated decadal variability. Looks like the IPO is transitioned from negative to positive. We should start to see this expansion of Antarctic sea ice slow down and perhaps even reverse. So Jean-Francois mentioned making plots and depicting uncertainty using these multimodal ensembles. This is just examples from the IPCC AR5. This is a figure that's a fairly standard type of figure that's appeared in all the assessments, but this is a particular version of it. These are surface temperature changes in a low scenario and a high scenario, and of course the colors are darker in the high scenario, meaning you're getting more warming. The number of models are these numbers here in the upper right-hand corner. So see, we're getting more than 30 models that go into this multi-model ensemble average. The colors are the sizes of the anomalies in degrees C, but this stippling and hatching is denoting a little bit more information. So stippling means that the multi-model mean is more than 2 standard deviations of natural internal variability in 20-year means. That gives you some idea of the significance of the size of these anomalies. And the hatching indicates the multi-model mean is less than 1 standard deviation of natural internal variability in 20-year means. But you're only plotting stippling and hatching where at least 90% of the models agree on the sign of the change. This is giving you information on kind of how seriously you should take the size of the anomalies and how seriously you should take certain geographical differences based on model agreement. Of course, model agreement doesn't mean it's right. That's kind of one of the other rules about these things. You're only indicating that the tools we have are giving you some information about where the models are indicating where we have the most confidence in these results. That's kind of a standard way of plotting, making these kinds of plots. So I was going to say a little bit about decadal climate prediction because a new feature in CMIP 5 were these initialized decadal hindcasts. So we had the kind of the standard scenario runs where we had the big 20th century and 21st century simulations and extensions out to 2300. But we also had this new field of decadal climate prediction, so we wanted to try to have a coordinated set of experiments that we could look at in a multi-model context with decadal climate prediction. So these decadal climate predictions were initialized with initial years starting in 1960. They were run for 10 years, and usually groups had ensemble sizes of maybe 5 to 10 members for each initial year. So in other words, you'd start the model out with observed conditions in the climate system, atmosphere, usually ocean. Say in 1960, you run the model for 10 years, you do several ensemble members, perturb it a little bit, and then you can compare that to observations, what actually happened. Then you go start in 1961, do the same thing, initialize the climate system and conditions in 1961, run for 10 years to 1971, compare to observations, keep stepping through all these hindcast years. This turned out to be a huge computational task, as you can imagine. We have multiple ensemble members from many initial years. But you have all these hindcasts where you can actually see how well you do in simulating this interplay between the internal variability and externally forced response. And the idea is that in the bottom here, can decadal climate variability processes and mechanisms, if properly initialized in the initial state where you start the model out, provide increased prediction skill, the time evolution, regional climate in the near term, over and above what you get from just the putting in the increasing greenhouse gases and things like that. So we're trying to now do both. We're trying to simulate the internal variability and the externally forced response in a time-evolving manner, just over 10-year periods. So these are some results from the chapter I was on, which was chapter 11, which is the near-term climate change chapter. So we were trying to portray this in several different ways. So we were given this near-term period. We defined the near term as the average of 2016 to 2035, so that's a pretty big average. But we tried to show how, again, in another way, this is the observations, and these are 4 observational data sets there with little error bars on them. And here are 42 models, 1 ensemble member per model, following the best practices. And you can see these are these individual blue lines. The models have certain spread. The observations are in the lower range of these uninitialized simulations that were started back in 1850 and freely running on up through the 21st century. Then we tried to show that if you put in this additional information from these initialized predictions. So here's a set of predictions initialized basically in 2006, and here's some that were initialized later in 2012. And you get some error bars here from these initialized predictions. You can see that they're in the lower part of the uninitialized model spread. So that's, of course, because you're initializing them in an initial state that's somewhat cooler because the rate of surface temperature and the rate of global warming has slowed down somewhat. And then we tried to come up with an assessed range of what the temperature projection would be for this time period, this 2016 to 2035 time period. And the conclusion was that this assessed range, taking into account these initialized predictions and other factors, was less than or lower than the uninitialized range, which would be this kind of gray shading and several different ways. So there we're taking advantage or taking into account the fact that we have these initialized, these new tools we can use to give us information that's different from the uninitialized predictions. Okay. Yeah, so I think you're forcing the models to start. Yeah, so your question is the effect of the initial state on the predictions, and that's exactly the important message from this figure, is that if you have a freely running simulation, you do a multimodel ensemble, you're going to get something that may not actually match up with what's happening if you have a period that's heavily influenced by internal decadal climate variability. If you initialize the models in that period, when you have something that's going on that's a big internally generated signal, you're initializing that information in the initial state, and your hope is that the model can kind of carry that through for maybe 5 or 6 years and give you additional skill. If you've got some slow set of processes or mechanisms that are producing this variability, the idea is that if you initialize that, if you start it out in the right direction, it'll kind of keep going and give you something that is better than what you'd get just from a freely running, non-initialized climate model. Of course, there's a lot of issues involved with this, but this is just an example of looking at these big decadal shifts that occurred during this hindcast period. There were 2 big decadal shifts of the IPO during the hindcast period from 1960 on, the mid-70s shift, which was studied quite a bit. And here's in the top panel, here's the observations, and this is looking at a 5-year average from 1978 to 82 minus 1961 to 75. And so we're going to look at initialized predictions that are initialized in 1976. So we're asking the question, how is this prediction 3 to 7 years in the future here differ from the previous 15 years that was already observed? The observations show this, of course, this big positive phase of the IPO, these warmer than normal sea surface temperatures over this 5-year average. Here's the multi-model average. I think this is 16 models. And you can see that the initialized models get this kind of positive phase of the IPO, opposite sign anomalies in the northwest and southwest Pacific. The uninitialized models show just kind of warming everywhere, so they're not giving you this kind of regional detail that you get from these initialized predictions. The early 2000s hiatus or slowdown, this is the observations looking at the period 2007 to 2011 minus the previous 15 years, and we're going to look at initialized prediction initialized in 2005. So you get this negative phase of the IPO. These temperatures are somewhat cooler than normal. And these are the initialized predictions for the same time period. It's not as strong as the observations, but it's definitely getting a little bit of cooling, and the warming is definitely less than it is. So you're getting an enhanced gradient across the equatorial Pacific. The uninitialized models for the same time period are showing kind of warming everywhere, if anything, kind of more warming in the east compared to the west. So these are kind of the things that people have been looking at from these initialized predictions. This is still early days in decadal climate prediction. First paper on decadal climate prediction was only published in 2007. And so this is really still the early parts of we're trying to understand what these decadal mechanisms are, how we can initialize them, do we get better skill, where do we get better skill? There's all these really interesting science questions that are involved in this really new area of climate science. So I've been talking a lot about multimodal averages and multimodal ensembles, but of course you can still look at single models. And so that for a while, I think there was some fear in our community that as these CMIP data sets became so dominant in our field, you wouldn't be able to get a paper published if you just had a single model. Because the reviewers would always say, well, yeah, that's one model, but what about all the other models? And why don't you look at all those? And that means you'd be forced to get a paper published, you'd have to do a multi-model analysis. But it turns out that single models are still useful, especially if you're looking at processes. And especially if you're looking at data that you may not be able to get from the CMIP-5 database, especially ocean data. So here's an example from another one from our group where we had this hypothesis that these big transitions in the IPO could be triggered by El Nino or La Nina events occurring. And the transition would be triggered by a buildup of ocean heat content in the off-equatorial Western Pacific. So this means we have to look at a lot of ocean data. And if you try to look at ocean data in the CMIP-5 data set, Carl may talk about this more, it's a lot of data. It's a huge amount of data. It's really a gigantic data processing job to look at ocean data. So we decided to use our CCSM4 because we had all the data here, and we were looking, in some cases, down even at monthly averages, which wouldn't be available in the CMIP-5 multi-model data set. And we said, okay, let's look at, if we think that this interannual variability can trigger a decadal transition, let's look at what happens in the initial states of our ocean in the off-equatorial Western Pacific. So we picked these two boxes in the off-equatorial Western Pacific and plotted ocean heat content down to the depth of the 20-degree C isotherm. And here's the mid-70s shift, the IPO transition. Here's the late 90s IPO transition. And here we are in 2013. And you can see that it seemed like the heat content was pretty high, and then it started dropping after this transition. Came down here, it was pretty low. We had this transition in the late 90s, early 2000s, and it's been building up again in both these areas. So when you look at these transitions, you come down here, and this is heat content in the equatorial Eastern Pacific. Here's the 76, 77 El Nino was coincident with when this kind of started dropping. Here was the 97, 98 El Nino, but more importantly for this transition was the 2-year plus La Nina that occurred afterwards. And now we're back to this state right here. So we said, okay, well, let's look at an initialized prediction. We can initialize the model in conditions in 2013 and see what happens. But we're prefacing all this on the fact that the model is able to get this interannual variability right, because the idea is that the interannual variability is the trigger for the decadal transition. So that means we got to at least get a couple of years of what's going to happen with the El Nino or La Nina sequences. So again, this is a depiction from our model, from the single model. This is the model initialized in January of 1978. We ran 10 ensemble members, which are the orange dashed lines. The ensemble average is the red line. The observations from the NOAA data is this black line. And you can see that it tracks pretty well. It gets the 76, 77 El Nino pretty well. And actually, the model stayed even warmer than the observations longer, which then contributed to this transition from the negative phase of the IPO to the positive phase of the IPO. Okay, so that's one example. Here's the early 2000s transition. The model initialized here in 1996, January of 1996. Here's the ensemble average from the model, the 10 ensemble members. Of course, the observations had this huge El Nino that was actually still within the envelope of the ensemble members, this particular model. But probably more important for the transition was this negative phase of these negative SSTs, and the ensemble averages stayed below normal for a couple of years, kind of like the observations did. And so it looked like, at least in a qualitative sense, the idea that this prolonged La Nina provided the transition to start accumulating heat content again in the western off-equatorial Pacific. And here's our prediction starting in 2013. It's going along. Of course, in 2013, there was a prediction for a huge El Nino in 2014, as you recall. Our prediction didn't get that, but it turned out it actually stayed pretty close to the observations. And of course, we had this huge El Nino that we're just coming out of. The model did get a bigger El Nino in the ensemble average than we got in 2014, and then it's going away here as we get into 2016. And this is the published version of this figure. I just decided to show an update of this to see how we did. This is what's happened since then, since we published the paper. Of course, the temperatures have dropped. We're coming back down to more of a neutral state. This may continue going down. It's hard to say. But I think the important part was we had this 2-year sequence of relatively warm conditions, El Nino-like conditions, that could have provided this trigger for a decadal transition. So when you look at the actual prediction, the pattern of predicted temperatures, here at the top is the prediction. This is the prediction average 2015 to 2019. So this is years 3 to 7 from the initial date of 2013, right? We're differencing it compared to the previous 15-year periods. We're asking, okay, how is this future period different from the previous 15 years? And you see this big positive phase of the IPO here in the Pacific, these red and orange, yellow colors indicating above normal sea surface temperatures for this 5-year time period. If you looked at persistence, if you just persisted the previous 5 years ahead to 2015 to 2019, you get nothing that looks like this because you're persisting the negative phase of the IPO. And if you look at the uninitialized free-running simulations with this model, it's just kind of warming up everywhere. So you're getting this regional differentiation that's quite a bit different and indicates that this transition probably occurred in the 2014 to 2015 time frame. So as you remember earlier, we were talking about how the IPO phase is connected to global mean surface temperature trends. We can see how these initialized predictions do. This is one realization of the observations here. Here's some initialized predictions going back here into 1996, 10 ensemble members. Here's from initialized, I think, in 2002, showing this slowdown in these ensemble members. And here's the initialized predictions for global temperature from 2013. And you can see that it's going up at a faster rate than they were back here. If you look at a few numbers here, the observed temperature trends from 2001 to 2014 was only about 0.08 degrees C per decade. Our prediction for this future period here is almost 3 times that, so 0.22 degrees C per decade compared to the uninitialized, and this is the uninitialized simulations up here, 5 members, ensemble average is the yellow line, the range is the max-min range for all the ensemble members is the gray shading. Initialized is about half of what the initialized prediction is, about 0.14. So stay tuned, come back in 2022, and we'll see how we did, which is the beauty of decadal climate prediction. You have to wait around a long time, and people may forget about what happened. So just to summarize, start out by just a few basics. The multi-model ensemble average usually outperforms any single model. And it also, these multi-model averages average out internal variability and gives you a focus on the forced response, which has positives and negatives, as I mentioned, depending on how you're trying to look at internal variability. To produce a multi-model average when there are multiple ensemble members of different sizes, you can do 2 things generally. Either you take all the models, well, first of all, you always take all the models in the multi-model ensemble and then use either one realization from each model, one ensemble member, and average those together, or you average all the ensemble members for each individual model and then average those together. The model ranking is kind of a red herring. It depends on the metrics you apply, and different metrics give different rankings. But you can subset models in the multi-model ensemble, and you can compute a multi-model average from this subset if you can have a physical justification for why you're picking that subset of models. There's new methodologies for weighting models, and you'll hear more about that in this workshop. Emergent constraints is another kind of new way of evaluating models where you try to relate feedbacks to something we can see in the observations. And I think that the other thing about comparing to observations is you should try to take into account uncertainty in the observations. I think Ben Santer is going to talk more about that on Thursday. But having said all that about multi-models, single models that are available in the CMIP 5 data are still useful to study processes. Thanks.